Hello, AP Stat students. Welcome to my first video. Sorry that I'm just getting it up now, but it's okay. We're all figuring it out here. So, a couple reminders for you is just check the blog constantly. I'm going to try and send y'all a remind when I upload videos to let you know they're up. But just constantly check the blog, videos, Khan Academy practice, and just kind of links to their videos also. I'll have the PDFs of the worksheets and like some check your understanding practices for you to try. There are the guided notes for the reading. It's very important that you're reading the book, okay? Don't forget to read the book. So these guided notes on there are for for you to use as you're reading. It kind of emphasizes the important things, okay? Your test information, if you haven't seen on the blog yet, your test is going to be on next Wednesday, March 25th. It will be on AP Classroom. We're going to open it from 7 a.m. to 11 p.m., but it will be timed. We'll give you 2 hours to complete it, which should be plenty of time. Just make sure you start it by 9 p.m. so you get those full 2 hours. It's going to be 15 multiple choice and 3 free response. All right. So that's just kind of a general overview. If I think of any other information to give you, I'll give it to you before the test. All right. So just kind of a brief overview of what's going on. So we're just going to get right to it. Okay. So, last week we had, we talked about our first chi-square test, our chi-square goodness of fit test. And remember, that's when we, that was with the M&Ms. And that's when we had a given distribution, okay? And we were comparing, so your chi-square goodness of fit is when you're comparing a distribution to a claimed distribution, okay, or a sample distribution to a claimed distribution. So you only have one sample, and you're just comparing it to what you've been told. So we're comparing the distribution of M&M colors to what the factory says the distribution should be. And we found strong evidence, remember, that our distribution was not the same as the claimed distribution. Okay, there was a difference. So today we're looking at a chi-square test for our homogeneity, where we collected data about favorite shows. So your favorite show preference from a sample, and on the paper, I'm pretty sure I added random sample on yours, but I printed mine already. A random sample of girls and a random sample of boys in pre-K. So do the girls' preferences in TV shows differ significantly from the boys' preferences? So if we look, we're given girls and boys, so our 2 different samples here of girls and boys, and our TV shows are Sesame Street, SpongeBob, Hey Arnold, Rugrats, and Paw Patrol. And we're given a little frequency table here. So first off, actually, let's go ahead and fill in our totals since it's there. I might be cheating and I might have already added them all together. So add these all up, we get 190. So we surveyed 190 girls in pre-K and we surveyed 360 boys in pre-K, 68 total like Sesame Street, 143 like SpongeBob, 111 like Hey Arnold, 65 like Rugrats, and 163 like Paw Patrol. And then combined, we surveyed at 550 kids altogether. So how is this kind of different from our goodness of fit test? Well, we now have how many different samples? We're actually using 2 different samples here, boys and girls. So girls and boys. So remember, with goodness of fit, we only used 1 sample and we compared it to a claimed distribution. Here we have 2 samples, but we still have 1 variable. Our variable here is your favorite TV show. So your TV show preference here. Okay, and this is 1 categorical variable. Categorical variable. All right, so this is how it's just a little different from goodness of fit test. We now have 2 samples instead of 1. We still are just dealing with 1 categorical variable. Here's TV show preference. Last week was the distribution of colors for M&Ms. All right, so now we still want to be able to find our expected value. Okay, what this means is if we got the same totals here, if we got the same totals, what would we have expected to happen here? So what we're going to do to get that is we're going to take the row total times the column total divided by the table total. Okay, so I'm going to go ahead and put my totals here just to kind of help me out. You don't have to do this. Oops. Okay. Because what we're assuming here is, and we'll find out in just a second, so we want to know if there is a difference between TV shows girls like and TV shows boys like. Our expected values are assuming that there is no difference in the distributions. Okay? So we would expect if there were 190 out of 550 girls, we would expect that ratio to be the same. What number should this be out of 68? So, and to do that, so if I'm just going to find girls who like Sesame Street. So I'm going to do the row total times the column total over the table total, or total here. And again, what it's really doing is it's taking this ratio, multiplying it by this to see how many would we expect. So 190 times 68 divided by 550. So we get approximately 23.5. All right, say we try now boys who like Hey Arnold. So boys who like Hey Arnold. So here the row total, 360 times the column total divided by the total total. So 360 times 111 divided by 550 is approximately 72.7. So you see this is a little tedious, but it's not awful. A little tedious, not awful, but I'm going to go ahead. It would be a long, boring video if I just kept doing all this math. So I might have already done it. And we're just going to write these in right now. So once I write these in, if you need to pause it, you can do that. And these are all, that's a 2. That's a 2. These are all the expected values we would expect to get. So there's our table. Again, that's a 2. All right. And so that's how we got our expected values. Row total times column total divided by table total. All right. And now let's start actually our full significance test here. So our hypotheses, remember, is always there's no difference. Okay. So we are going to say here, and you'll find with all chi-squares, goodness of fit, homogeneity, and tomorrow we're going to look at independence. You're going to find with all of them that you're actually going to have to write something else, not just going to be in numbers or variables, things like that. So we're going to write it out. And so this is going to be, we're just assuming that the TV show preference for girls and boys is going to be the same. Okay? Or you could say there is no difference in the distributions of TV shows between boys and girls. So, again, there's a few ways to write it. So I'm just going to write, let's see, what do I want to write? There is no difference in TV show preference between pre-K girls and boys. And then the alternative will be there is a difference in TV show preference between girls and boys. Pre-K girls and boys. Girls and boys. All right. Again, you can say it like this, or you could have said it like the TV show preference is the same for your null, and the TV show preference is not the same. So whichever way you prefer is good. All right. Let's go ahead and let's just use an alpha of 5%. All right. Let's use an alpha of 5%. And let's now look at our conditions. Let me get this out. So for our conditions, it's pretty much the same idea as your chi-squared goodness of fit. All right, so the first one we're going to check is our random condition. Now remember, in this case, we are looking at 2 random samples. So just make sure you emphasize somewhere about both samples. So it does say random sample of girls and boys. All right, so that condition is good. Now, for our 10% or our independent condition, sometimes they could just be independent events, but here they're not. We don't have replacement. So 10% condition, we have 190 is less than 1/10 of total pre-K girls, right? And then 360 is less than 1/10 of total pre-K boys. And what I did here is I just took the totals of my 2 samples. And then let's talk about large counts. Remember, with chi-squareds, we don't want to mention anything about normal because we'll show the picture in a second, but remember, this is not a normal curve, okay? So don't mention normality here, but we still have to talk about large counts. So let's look again. Look at our expected counts here. Were they all greater than 5? Yes, they were. So we know all expected counts are greater than or equal to 5. And then you just have to show me the smallest one. So the smallest which in this case, it looks like girls who like Rugrats is 22.5. So the smallest is 22.5, which is also greater than or equal to 5. All right? So don't forget that. So those are our conditions. Now, your specific formula is the same for chi-square goodness of fit. Your chi-squared is the sum of the observed minus expected values squared over expected. So observed minus expected squared over expected. So let's actually write out our work here. So to get our chi-squared, I'll go back to my little picture here. So we observe, for instance, girls who like Sesame Street. There's 20 of them. We expected there to be 23.5. So we're going to say 20 minus, oops, no, why did I put parentheses? So 20 minus 23.5 squared over 23.5. That's a minus. And then now I could do this 1, 2, 3, 4, 5, 10 times. Or to save us some time, we're going to write the first one, and then we're going to write dot, 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 and then we're going to write the last one. So it looks like the last one are boys who like Paw Patrol. So if I went this way, so there's 109 boys that like Paw Patrol. We expected there to be 106.7. So 109 minus 106.7 squared over 106.7. Now, since there was a lot of data here, a lot of different categories, this would be pretty tedious to find. Easy, right? Easy to set all this up, but just kind of obnoxious to plug into the calculator. So in a second, once we're done with this, I'm going to show you what to do, kind of our little shortcut buttons for you to get this number, okay? So I'm going to go ahead and give it to you. Our chi-square test statistic is 10.187. So just write this down. We'll come back to this in just a second. All right, so now with your goodness of fit, your degrees of freedom was the number of categories minus 1. This is how we find the degrees of freedom here. The rows minus 1 times the columns minus 1. And it makes sense because, well, let's calculate it and I'll tell you why it makes sense. So we had 2 rows, girls and boys. You're ignoring the totals. We had 2 rows, and then we have 5 columns. So 2 minus 1 times 5 minus 1. 1 times 4 is just 4. These are our degrees of freedom, which makes sense because if you were given 4 of these and the totals, then you could find all the rest. So you need at least 4 numbers to be able to find the rest of the numbers, okay? Our picture, remember they're all positive, so it starts at 0. And I showed you a picture last week. Depending on how many degrees of freedom there are, it looks a little less intense, right? But it's going to be right skewed. And our chi-square test statistic is going to be somewhere at this tail. Remember, always looking at the tail or greater. So somewhere over here is our chi-square test statistic. Okay? And then we know our chi-squared is 10.187. And we now need to find our p-value. So I wonder, let me go grab my textbook. All right, so here's the textbook. Now let's talk about a couple things with this. We're on table C. This is also in the back of your textbook, or of course you can always Google your chi-square distribution critical values, and you'll see plenty of these. This will pop up quickly, okay? So first of all, we got 10.1 something, 187. So let's talk about that. We have 4 degrees of freedom, and our critical value is 5%. So this is kind of where the rejection zone starts at 9.49. Well, isn't 10.187 greater than that? So it's kind of farther along in the tail. So just by comparing our critical value with our chi-square test statistic, we see that we're going to have to reject the null, right? But we're going to look, since 10.187 is somewhere between here, our p-value will be somewhere between 0.025 and 0.05. Okay? Oops, right here. So that's one way to do it. But now I'm going to show you what to do in the calculator. All right? So, and then we'll write our conclusion. All right, so hopefully you have your graphing calculator with you. Make sure it's charged. And so here, since we have a frequency table here, a two-way frequency table, we're not just going to go and put our data in the list like we did for our goodness of fit. We're now going to go and put it in a matrix. So what you're going to do, you're going to push second, x to the -1. Oops, you can't see my buttons. Second, x to the -1. Right above it, it says matrix in blue. Okay, and then you see all these matrices that you can use. I'm going to click the first one, but we're first going to go to edit. So scroll over to edit, and then let's just click matrix A. So it gives us dimensions. We have to type in the dimensions. Well, this is a 2 by 5. Again, don't include the totals. So it's 2 by 5. And you see, as soon as I do that, it's kind of a glare on there, sorry. As soon as I do that, it brings up a 2 by 5 matrix. And we're just going to plug in the numbers exactly as we see them in the right, same order and everything. And this is of your observed data. Okay, this is your original data here. Okay, and now the cool thing is you don't need to type in your expected matrix. It will do it for you. So once we type this in, let's go to our magic button, and that is stat. Scroll over to tests, and then it is your actual chi-squared test. So don't click on the goodness of fit one. Now, even if your calculator is very old, you will have this test. Remember, some of you might not have had the goodness of fit test, but you should have this one. So everyone click chi-square test. Now, observed is where your matrix is going that we just typed in. These are the observed values. Now, expected is just telling you where you want the expected matrix to go. So the cool thing is it will give you your expected values. It's going to calculate them for us. I'm going to go ahead and draw this just so we see what's happening. You can see kind of the chi-square curve that's occurring. Can you all see that? Oh, no. Maybe there. Okay. So you kind of see the chi-square test that's happening. It's skewed to the right. Okay. But you see the shaded tail. Oh, there we go, maybe. You see the shaded tail? That's where 10.187 is. Okay, and we shade to the right. So this is, there's your graph. So we're going to go back to chi-square test. It's option C in my calculator. And then let's actually go now to calculate. And look, it actually gives us our exact chi-square, 10.187. And then it has our p-value of 0.0374. Okay. So your calculator will give you your exact p-value. Your table C will give you kind of a range of where it's going to be. Okay. And it has your degrees of freedom here also. So our conclusion, since our p-value of 0.0374 is less than our alpha, we reject the null. We have convincing evidence that the TV show preference is not the same, or I guess that the distribution of TV show preference is not the same between pre-K girls and boys. All right, so you just completed your first chi-squared test for homogeneity. All right, so just some quick big ideas that we're going to take from this for your hypotheses. Your null is always going to be something like there is no difference. The distributions are the same, okay? In the blank, which is, where's my other colored pencil? So there's no difference in the categorical variable distribution for your two different populations. And your alternative is there is a difference. Blah, blah, blah. In the categorical variable distribution for your two different populations. Now, always make sure you're using context here. Always, 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 always be specific, all right? For your expected counts, remember it's your row total times your column total. Total divided by the table total. Your degrees of freedom is just the number of rows minus 1 times the number of columns minus 1. And then the differences so far for a chi-square goodness of fit, it is one sample and one variable. Okay? And we're comparing it to a claimed distribution. And then today we looked at a chi-squared test for homogeneity. And it's two samples, but one variable. Okay, so what I want you all to do now is go back to the blog, print out the Check for Understanding worksheet, and see if you can try that in just a little bit. I'll also have the answer key up so you can compare for that. All right? Good luck. You've got this. Let me know if y'all have any questions by email or every school day from 10:30 to noon. You can hop on my Microsoft Teams chat and ask me any questions there. All right. Bye, y'all.